Hello everyone, I'm Jerry from Clermont-Auvergne University. I'm glad to make a presentation here. The title is PCMO Partial Classification from CNN-Based Model Outputs. At the beginning, I will introduce the problem, solution, and motivation, following its background. For example, Dempster-Schiffer theory, then its contribution. I will introduce the proposed method and framework. Then its experiment includes experiment protocol, evaluation of the proposed method, and practical usage. Finally, its conclusion. What's the problem? Suppose we have three classes and a sample. As we can see, we can't manage to reliably classify it into a single class, but it's almost sure that it doesn't belong to first class. So how can we deal with such a situation? The solution is partial classification. It's more reasonable to assign it to the subset composed of second and third class. What's the motivation? There are three main directions of the existing method. Each has their advantage and disadvantage. The first one, predict a fixed number of classes, such as the top 5 most proper classes. However, there is no reason to predict exactly 5 or any other prior fixed number of classes all the time. Second, classification with reject option by assigning outliers to the empty set of the entire set, reflecting maximum uncertainty. It can be seen as a special case of partial classification by giving belief for one specific class subset. Third, modifying loss function or building the new classifier to provide beliefs for predicted sets. It's necessary to reduce the computation and time complexity. So we want to fulfill partial classification only based on model outputs, neither retrain the model or conduct any further modifications. Here are some notations we are going to use. We have key class. Each sample has D attributes. A class subset composed of key class. The training dataset, last hidden layer, the output layer, the loss function, and the model. Dempster-Schiffer theory is used to calculate the belief. The belief function applied on a sample measures the degree of belief that the ground truth level of this sample belongs to a subset. It satisfies the following equation. The subset such that belief greater than 0 is called the focal set. When the focal set is nested, the belief is said to be consonant. Now, I'm going to introduce the proposed method. The model mentioned in this article respects two usual and reasonable assumptions. First, the model loss converges to 0 when the interaction T approaches infinity. Second, the model's left hiding layer and the output layer are fully connected. Before going deeper, let's have a look at the pattern of CNN-based model outputs. We use two classes, MNIST and CIFAR10. The model used from left to right are LeNet, GoogleNet, RaceNet, and MobileNet. As we can see from those two figures, a sample far from the training dataset can bring high outputs and lead to high probabilities for several classes. Under this context, partial classification rather than precise classification should be used. Since we want to fulfill partial classification only based on model outputs, it means we need to calculate the belief from model outputs. However, there is not a transformation from output to belief, so we take a possibility as the bridge. First, sorting output by descending order and calculate a temporary vector, which is used to calculate the possibility. In this equation, as we can see, The divisor is used to penalize the ambiguity caused by classifying sample to subset. At the same time, in order to avoid the negative possibility, we clump the outputs greater than 0 and move the log curve to left by 1 unit. Then we can calculate the belief based on the possibility and fulfill partial classification by choosing the subset with the maximum belief as the prediction. Here is the framework. As we can see, there are two parts. The CNN-based model extracts features from the input layer. Then our method transform output to possibility, then transform possibility to belief, and fulfill partial classification based on the belief calculated. During the experiment, we use several classes. For example, MNIST and CIFAR10. Methods for comparison are dropout, ensemble, and energy score. Models involved are LearnNet, GoogleNet, RaceNet, and MobileNet. We use two criteria. The average discount accuracy is a single value, with the requirement that the better the prediction, the larger the average discounted accuracy is. To be sample hereafter, we will call it accuracy. In addition, we also use expected calibration error. The smaller, the better. First part is evaluation of the proposed method. Naturally, the bigger cardinality of the predicted set indicates a more confusing input sample. Thus, in order to verify the efficiency of partial classification and the capacity of reducing the classification risk under the proposed method, we rejected the most confusing samples according to different rejection rates. As we can see, we test 4 models based on different datasets, MNIST and CIFAR10. From the figure, we can see, first, the accuracy increase along with the increase of reject rates. Second, the selected 4 classical models achieved good accuracy values, except for the slightly worse initial accuracy of LearnNet and MobileNet due to its sample model architecture. On the other hand, we verified different methods based on GoogleNet. As shown in these two figures, our method increased significantly when the reject rates increased from 0 to 0.1. In contrast, the accuracy of the other methods performed fluctuation or insensitivity when the reject rate increased from 0 to 1. To show the efficiency of different methods and models when against a small reject rate, we set reject rate equals 0.1 for different model and different methods. As we can see from those two tables, our method achieves the highest accuracy and comparable expected calibration error among all the methods. This table displayed the detailed performance improvement compared to other methods. The second part, in order to prove our method is effective in reducing classification risk, we applied it to the root surface classification. The root surface dataset is mixed manually from Crack and Putol datasets. As we can see from this figure, it contains 3 classes, Crack, Putol, and Normal, and in each class, there are some confusion samples. On the one hand, the first line shows the certain samples. For example, the first image represents crack. As we can see, the crack area is obvious and clean. So our method produces high belief and low uncertainty to indicate the certain classification. On the other hand, the second line shows some confusion samples. For example, the second image represents a Putol sample, but as we can see, is similar to a normal sample. So our method produces low belief and high uncertainty. Based on our method, we can reduce classification risk and enhance the quality of target system by rejecting confusion samples. Finally, its conclusion. We adopt the possibility as the bridge, fulfilling transformation from model outputs to beliefs for the predicted set. Make a partial classification by choosing the subset with the maximum belief. Second, from the production of two criteria, we can tell that our method performs better than the existing methods, as it can prove a high belief to a certain sample as well as a high uncertainty to a confusion sample. In the future, we plan to explore the feasibility of our method on all types of pre-trained models and try to develop a method to generate beliefs for all subsets of the entire set.
Thanks for your attention.